All right, I am Zion Leonahenahe Basque. I am a incoming assistant professor at University of Georgia. However, I did this work when I was at Arizona State University finishing up my PhD. I actually just finished it up this month, so I'm very happy to present this talk again. Some parts are from NDSS, where this paper won a Best Paper Award, and it shows off a lot of the work of understanding how do people reverse engineer and what does it look like in this modern age of large language models. I really like the order of these talks because as the last talk with Zach was talking about dynamic analysis for kind of reverse engineering and finding vulnerabilities and things like that, this talk is mostly on static analysis. But let's kind of get into why that's important and why that matters. So I'd like to first start with talking about the real goal of reverse engineering or doing any of this analysis of programs in general. And it's that we are trying to secure critical software. Whether we are doing that offensively or defensively, we have many different devices which we are trying to understand and figure out if they are secure. Now, it is no surprise that most of these kind of targets are really hard to understand when you look at them as a third party or as an analyst. For instance, you might have something like a pacemaker or some operating systems on a computer or an autonomous car. And these are all deployed as binaries, which are fundamentally harder to understand than normal programs because they are stripped of semantics and they no longer look like what the developer actually made them, whether they're in an adversary or an ally. These kind of things become hard to understand once we hit the binary level. And that's bad because we need to secure them. So traditionally, these binaries need to be taken up by experts or security practitioners in your own teams to achieve these downstream security objectives, such as malware identification, such as program reconstruction, such as vulnerability discovery. These are all things we aim to do given that binary. And that process of actually getting there, creating a understanding of the program is what you need to do first before you can actually achieve these security objectives. So on the way to maybe identifying if this program is malware, you need to first figure out if this program is a server or how it's connected, how the different pieces relate to each other. And this is called building a software understanding, a understanding of what this software does. The process of building that software understanding in a program that you don't own or you didn't create is software reverse engineering. And it is critical to securing these types of binaries or software that we didn't have or don't have the source code to, or things we just don't understand what they do. And so in our study, we aim to understand this process of reverse engineering. To give you a little bit of a background, there's only been a very minimal set of works that have investigated humans in reverse engineering. Most of them have concluded that this is a human-dominated task, i.e., although we have many automations such as decompilers or symbolic execution or even emulation, most of reverse engineering is done by a human because it is just that hard. Additionally, it is incredibly expensive because it is human dominated. It takes a lot of time and money to actually reverse engineer software, whether it is a firmware or whether it is even a user space program. This is a very expensive process. And anybody who's had to train up these in their organizations or had to pay people for it would know just how expensive it can be. And it's that expensive because aside from just being human dominated, reverse engineering is expert driven, i.e., novices who try to enter into this field are going to have a lot harder of a time actually showing value to people who need to secure the software. Because reverse engineering is very hard and it comes with different kind of flags and ideas that only experts notice after doing this for years and years of time. And so many reverse engineers across the world, starting back in 2023 when ChatGPT first released, were looking for ways to speed up this reverse engineering process. After all, if it is so expert driven and so expensive, is there ways that we can kind of shave off time or shave off understanding difficulty by using a large language model? And so we noticed in 2023, security practitioners had started integrating these large language models to build a software understanding for them, or a idea of how different components in the same software relate to each other. Now, to give you a kind of concept of what that looked like, we need to look at this concept of software understanding more. What does it mean to actually build a understanding, and how does one do that while reverse engineering? Well, you can think of this whole software understanding task as a series of reverse engineering tasks that we can break up into kind of step-by-step processes. For instance, one task you might do in reverse engineering is symbol recovery, which is a type of way to kind of summarize what things do, whether it's a function or a variable, because these are stripped out in the compilation process. Another one is type recovery, where you try to understand abstractions such as classes or such as primitive types to understand the intent of different areas of a program. Another one might be commenting, where you try to summarize something like a normal software engineer might do. And these are all different reverse engineering tasks that your average reverse engineer will encounter when they're trying to understand a program they did not make or they're trying to secure. And so a lot of previous research had investigated how can we use large language models to improve these individual tasks, like symbol recovery. So using a large language model to recover variable names, including some of our own previous work, or using it for type recovery, or using it for comment recovery. These are all different individual tasks people had used large language models for. But no one had quite investigated how all of these tasks are related and how the whole process changes when an LLM is involved as a teammate. So we wanted to investigate this higher level process because we know from experience that when you're recovering a symbol, this is not actually a independent task. You also recover types. You also recover comments, i.e., this process of reverse engineering is iterative by nature. And so we wanted to study how do all of these intertwine with each other and how does it change when a large language model gets involved as a teammate to help a human reverse engineer software. Now, to do this, we had three fundamental research questions we aim to understand about these large language models in the reverse engineering process. First, how do practitioners actually use LLMs for reverse engineering? How is it integrated? How are people interacting with them? Since at this time and even now, there wasn't a lot of quantitative information about how practitioners and teams are using LLMs for reverse engineering. The second one is how do LLMs actually impact reverse engineering performance once we know how they're used, i.e., are they actually positive or are they negative? Since there was no quantitative information on do LLMs actually help people, it was kind of all vibes at the time. And additionally, do the ways that these different practitioners interact with LLMs actually influence this downstream reverse engineering performance? Because many different practitioners that had reported using an LLM had considered themselves either experts in using LLMs or novices in using LLMs. And we wanted to understand if that difference actually meant something when they were reverse engineering. So, to answer those three questions, we designed a three-phase study that started in 2023 and expanded all the way till 2025. In these three phases, we had different components to build this infrastructure for understanding how humans reverse engineer. In phase one, we conducted a pre-study survey online with 153 different practitioners to understand how they were using large language models and how this actually helped them or hurt them during their working process. Then in phase two, we designed two CTF challenges based on the feedback from the survey that we would then use for these different practitioners to show us how they reverse engineered in real time. Finally, a subset of that 153, 24 experts and 24 novices, we invited to do a human study where we watched them as they reverse engineered two different softwares that we had created, and then they submitted write-up. We would see this as they use large language models and as they didn't, so we can analyze how are LLMs actually affecting this reverse engineering process. Now, to kind of condense this time frame of, or to condense for time of all the things we did in this study, I'm only going to talk about phase one and phase three, so you can see the results of our study and how this kind of impacts downstream performance. In phase one, with this pre-study survey, we had 153 survey responses, which revealed six distinct ways that these different practitioners were actually using LLMs actively in the reverse engineering space. For all six of these applications, reverse engineers reported using them across different decompilers. So they would take decompiler output for a binary and they would put that into ChatGPT to do six distinct tasks. These were the six distinct tasks. You can also find more about these in our paper, but generally all of them had to do with recovering information in a faster way, such as function summarization or variable symbol recovery, all of these with the exception of vulnerability identification, since these challenges would have vulnerabilities in them that these different reverse engineers had to find. And so we found from this survey that people were actively using it for these main six purposes from 2023 up till even now. Now, given that information, we designed two CTF challenges inspired by reversing real programs and to be reversed by decompilers. These two challenges would have vulnerabilities in them, and it would be like a capture the flag challenge. Now, to give you an idea of what these two challenges were like, the first challenge was an RPC server, which had various flaws in them. For instance, how you talk to it, there was a flaw in the encryption where you could break the key with certain information. The second program was an encrypted file system manager. You could imagine this is something like Bash, but specifically for decrypting and then re-encrypting files on your own file system. Both of these two different programs had vulnerabilities, and it took a while for our different reverse engineers to actually find them. In total, these two challenges were about 900 lines of C code, and we had various metrics to see if they were equivalent, i.e., different software understanding metrics like is it the same complexity of programs? Are they the same length? Do they look about the same difficulty, which we tested over time before we deployed to our participants? And finally, when we gave all of the participants these challenges, they were in binary form, they were compiled, and they were stripped. So these were very much like what you would experience while reverse engineering real software. If you're interested more about these challenges, you can find them in our own paper. We also had a post-study survey to make sure that experts thought these were actually indicative of what they might experience in real life. Now, to give you an idea of what these reverse engineers did in our human study while we analyzed them, it looks something like this workflow. All of the reverse engineers in our study had access to a decompiler. The decompiler they had was IDA Pro, since it was reported as the most used decompiler by practitioners in our pre-study survey. This IDA decompiler was heavily instrumented, so we could see everything they did during the reverse engineering process, including variable renaming, including clicks, including moving around the decompiler, creating structs. We could see quite literally everything they did. And in addition to that, we also had a screen recording of everything. So we had a lot of data that we could automatically collect from these participants. Once a reverse engineer, one of these practitioners, went into the study, they had access to a large language model, and then they had access to the challenge binary, for which they would try to solve by capturing the flag, and then submit a solution description. So after reverse engineering it for an hour or two, they would write up a description of how to actually solve it, which we could then reproduce later. Now, to make this as accessible as possible, since we wanted to analyze how experts reverse engineered in our study, we had to make this remotely accessible. And so it was built on top of Pwn College. Through Pwn College, these different participants could actually access a virtual network computer, this desktop, where they would have access to our instrumented version of IDA Pro and our LLM tool, which they could use for various tasks. Looking at this slide, you can actually see how people saw it. So this would be if they were using Google Chrome, they would see this in their browser, which is IDA Pro on a desktop, and they have access to these different LLM features, which you can see when they right click, which are on the bottom right here. These are the different features. For instance, you can see they're about to select summarize the function, which would summarize this current function they are looking at IDA Pro and put it in the comments of this header. One thing they might ask is something like, does this function contain a vulnerability? And that information would then be responded to by the LLM and put into these comments of the function, ideally to help them find if there was a vulnerability or not. So participants could use any of those 6 features that they had reported earlier to us, or in the more extreme case, they could also do a free prompt, which is shown at the bottom there, where they just talk to the LLM directly without any of these pre-constructed prompts. Now, the study, to be more scientific and to understand if LLMs actually were making an improvement or degradation for these practitioners, we had both a control and treatment group, which was the participant themselves. Every participant would do 2 challenges. Both challenges were approximately equivalent in difficulty. On the first challenge, for instance, they might not have access to an LLM, and that would be a control group. On the second challenge, they would have access to an LLM and a different challenge, and that would be the treatment group. This allowed us to compare people against themselves, but also against each other. So we could see expert-based improvement or novice-based improvement and just kind of challenges between each other. And that was generally how we did this setup and why we had 2 challenges, so that we could do this test between having an LLM and not having one. Finally, this kind of last idea of how we design the study, we had to design how we rate if people are doing a good job or not. For instance, if when someone is using a large language model, did they actually get improvement over themselves? And to do that, we had to create a new metric for quantifying software understanding, or this process of knowing how the binary works. In previous research, and what you might find on many benchmarks nowadays, they looked at this as a binary problem. For every practitioner, the practitioner either created a solve script and got the flag exactly, or they did not, a 0 or 1 solution. We found from our own experience in reverse engineering, this is not actually true and not reflective of reality. Oftentimes, people can have a very high level of understanding, but maybe be just a little away from having the final exploit script working. And we wanted to understand how people had this understanding, even if they didn't fully solve the challenge. And so we considered that solving a challenge looked less like a straight line and looks more like this kind of up and down of progress of understanding this binary and getting an actual reverse engineering progress in it. These ups and downs could be represented by checkpoints. Either they got something right or they got something wrong. In the two challenges we created, there were 8 checkpoints. An example of a checkpoint would be for the RPC server challenge, knowing first that it is in fact a server and the way you interact with it is over a network. And second, that maybe to interact with it, you have to be first base 64 encoding all of your packets and then sending that over. These were different understanding checkpoints that were required to actually make it to a final description. We could take the checkpoints that people got correctly over time, and this created our fundamental metric in our study, which is the software understanding rate, or how fast are people getting to critically important areas of a program, since all of these checkpoints are necessary for someone to actually solve it and exploit the final vulnerability in these CTF challenges. Now, with the design out of the way, I want to give you a quick overview of the study and how many people we had and how much time it took. We had a total of 48 participants, 24 experts and 24 novices. These all were self-reported and then verified later by their experience and how fast they actually reverse engineered, which we found to be reflective of what they reported. Together, these two had created 109 hours of recorded reverse engineering progress and instrumented progress we saw within the decompiler. So it is a lot of data that we went through to understand how LLMs are actually affecting people while they reverse engineer. It also included 1,517 LLM queries, 728 by experts, and 789 by novices. What this really says is people used an LLM in total 1,500 times. The first interesting thing I want to note here is that between experts and novices, they actually used an LLM almost the same amount of times, which was non-intuitive for us because we expected experts to be much less reliant on LLMs than novices. And so this was kind of the first takeaway of our study was that people are actually using LLMs the same amount, regardless of how good they were of reverse engineering. But the next question you might have is it actually helpful? Are people getting real benefits from using these large language models? And in fact, many people did. We found that these large language models were actually closing the expertise gap. For novices that used large language models during the study, they showed a 2 times increase in software understanding rates while using a large language model, which actually approached expert levels of reverse engineering while they were reversing binaries, which means these LLMs are fundamentally closing this expertise gap in performance. When we looked deeper as to why exactly are these novices doing so much better than they were prior to having LLMs help them reverse engineer, we saw that most of this was actually due to function summarization. Here's one example of what that actually looked like. Here is a function that almost every expert in reverse engineering recognizes within a few seconds. Prior work has called this a beacon, something that you kind of generate over time with just a lot of experience. If you're unfamiliar with what this function actually is, don't worry, it takes a lot of expertise to know it immediately. This is the T encryption algorithm or tiny encryption algorithm. And for novices that use an LLM, within the first 10 seconds of visiting this function, they were able to identify that this is in fact the T algorithm, which was great because that meant they could skip it immediately because they knew the vulnerability wasn't here. This is just the common implementation of T. And so that allowed them to have a significant speed up in reverse engineering. They fundamentally got to access expert level knowledge without actually being an expert, summarizing functions they didn't know. Now, that was great, but you must be wondering if novices did so much better from this kind of condensing of knowledge they didn't originally have access to, did experts actually find an improvement while using large language models? And unfortunately, experts had a negligible reverse engineering improvement while using large language models. So, although experts and novices actually use these LLMs the same amount, they disproportionately were getting improvements. Experts got almost no improvement from using large language models. We saw no significant difference in their improvement status. And it generally showed to us that this model of collaboration isn't actually helpful for experts, which not many people knew at the time that experts don't actually get as much from this than novices do while reversing, right? Because they use it the same amount, but they got it for less benefit. When we looked deeper at this, we found that most of this was due to a kind of faulty collaboration model that experts just didn't need. Most of this study showed LLMs used as a tool where they kind of used it in the middle or at the start of the reverse engineering process. But many experts didn't want this style of collaboration and looked for something else. Instead, this caused a lot of slowdown for them, which showed a negligible amount of improvement. We looked a little deeper at this collaboration model flaw. Are people actually getting worse performance when they use an LLM and collaborate with it? And in fact, we found that was true. For all the participants that used a large language model in our study, the ones that collaborated with it more or kind of iterated on it, so i.e., they use an LLM on a function and they keep going back and forth with it, trying to refine it, they actually showed a lower overall understanding rate, indicating to us that these large language models aren't actually teammates for many of these people. They're just kind of a summarizing tool that either works or it doesn't. And when people try to collaborate with them like they are teammates, this created much worse performance for those individuals. Additionally, we found that we saw something we call the first look strategy, i.e., using a large language model in the first few seconds of ever seeing a function. This was actually the dominant strategy for getting any improvement with large language models, i.e., if a reverse engineer enters a function and they use a large language model in those first 60 seconds of seeing the function, that was likely the only time they got improvement using a large language model. If they used it later, let's say 5 minutes after looking at the function, they likely saw no improvements. This all generally indicates that the current way LLMs are being integrated are not as teammates and not actually as collaborators. They're actually just tools that are either faulty or good in very specific scenarios, i.e., if something was compressible, like I showed with the T encryption algorithm function, then it was compressed into knowledge rather quickly. But if it wasn't, then you never got it, and you instead just wasted time trying to make an LLM give you something that it just fundamentally didn't know. Now, the final thing I want to look at is I showed you a lot of benefits of people using large language models in this reverse engineering progress, but I want to talk briefly about the risks that still remain with even the best large language models on the market now. Of the 1,517 LLM responses that we saw in our study, we only saw three hallucinations across every LLM response. And if you asked any AI expert right now, they would say this is a awesome metric, right? This is only three hallucinations out of 1,500. That is less than a 1% hallucination rate. However, this is not showing you the true story of the damage of these three hallucinations. These three hallucinations were encountered by three different participants during our study, and all of them were on the task of identifying vulnerabilities in the binary. So it was a hallucination where there was no vulnerability in this function, and instead the LLM said there was a vulnerability. For all three of these participants, this caused a minimum of a 231% understanding rate slowdown, which is really quite bad. But more important than just the slowdown, this actually caused damages to the final report that they submitted. For all three participants that encountered this hallucinated vulnerability, they submitted an incorrect solution early and said that they had found the 0 day, they had found the vulnerability in the binary, submitted to us, and said, I'm done, I've completed it, everything looks right. This might not be a big impact in a CTF, but for real world scenarios where you are using large language models to identify vulnerabilities and then submitting an incorrect report, this can be fundamentally and critically bad, i.e., these LLMs can be very dangerous in security critical situations where we must show correct information. Even though they have such a low hallucination rate, this can have disproportionate amounts of damage and requires us looking deeper at how we can maintain LLMs being useful to real practitioners for real security applications. To give you a hint, though, as to why this happened, it shows that we need research across many different domains, not just a human study and not just program analysis or AI, but the overlap of all three of these. To give you an idea of why this happened, this is the real line in the source code that you would have seen if you had the source code and used an LLM on it. It is simply a 1 byte assignment to a 1 byte buffer. This is exactly what it looked like. But for all three of the hallucinations, this is what the decompiler showed them. This is what IDA Pro shows. It's a very kind of lossy line in decompilation. It's just fundamentally bad because decompilers are still bad. They're estimating what the source code was. When a large language model encountered this line of decompilation, which is not an overflow at all, it perceived it as an overflow because the decompilation is lossy and it looks broken when compared to the source code. This shows again that large language models are not perfect collaborators and they're not humans. A human would not get tripped up on this, and it requires more research across all directions to make sure that they don't. If we improve decompilers, for instance, this will fundamentally improve their performance on downstream reverse engineering tasks. So there's a lot of future work that can still be done in this area because this is really the first human study in analyzing how LLMs are actually improving reverse engineering, which can be critical to our national security or to general transparency in understanding software. For future work, there's a lot we need to do. For instance, quantifying and evaluating the effects of these decompilers downstream. For instance, our entire study was on IDA Pro, but if you're using Ghidra for the same task, it is likely you did much worse because generally speaking, Ghidra has a lower quality of decompilation than IDA Pro. Additionally, applying this software understanding metric, what we had created for this study, this fundamental new metric for understanding how people are understanding software, can actually be applied to LLMs without humans or full autonomous reverse engineering, giving us a way to quantify if LLMs are actually here, if our adversaries already have the ability to understand software as if they had an army of experts. And finally, investigating new collaboration frameworks. Recall that experts didn't benefit much from actually using an LLM. This indicates to us that there is a completely different way that experts actually need to interact with LLMs while reversing to get real improvement and to show real benefit to them, which we must investigate because experts are our first line of defense for different kind of cyber operations. Finally, I want to summarize about what our study did and what information you could find if you want to check out our paper later. We conducted the first empirical study on software reverse engineering with large language models, creating the first information you might find about how they're actually benefiting or hurting different practitioners while reversing. We also created a methodology to quantify the understanding of software in reverse engineering, and that illuminated 18 different findings you can find in our paper. And finally, we open sourced our platform, either through Prone College and through GitHub. We have all of our LLM tools. You can find all of this online at Mahalo/Dex Synergy Study, which there will be a link to the slides and the slides will be shared. You can go check out our platform. This also produced a tool that many people use right now called Dyla, which is for using this LLM features I already showed in the study. A lot of practitioners use it now. It has over 680 GitHub stars and over 1,000 PyPy installs a month. And on that note, I thank you very much for your time. Again, I'm Zion Leonahenahe Basque, an incoming assistant professor at the University of Georgia, and I'd love to take any questions you might have. Thank you very much. Okay, I see a first question from Jonathan. Many researchers have found that LLMs amplify expertise, increasing the gap between them and experts. You saw the opposite in your domain. I'm curious about your perspective on this difference with the other way. Increasingly, okay. Might other ways of LLMs in reverse engineering result in more benefits to experts? Yeah. So, Jonathan, I completely agree. The question about are there different ways to use LLMs to improve performance? Yes, we're already trying to do some of this research in the background to figure out are there different models. For instance, people are using an agentic workflow now where you have an LLM reversing on the side of you instead of you initiating when the LLM should do reversing, and then seeing how we can port that information back to experts. We think that this is a more performative way experts can use it. So, not initiating LLM use, but actually letting it just go wild like a normal human. This might be something that is more performative. It also comes with more risks because there's more ways for hallucinations to happen. But yeah, I think there's a big difference in how we can actually make this collaboration happen. What particular model did your experiment with? Okay. Yes, during our experiment, we gave them access to 6 different models. They could choose during the study and change it. This was back when it was GPT 4.0, and this was Claude Opus 3.5, I believe. We have all the different models in our paper. It was also Gemini, most models that you would find at this time in 2024 to 2025. I redid some of this experiment a few weeks ago too to make sure results are similar on Opus 4.6, and in fact that hallucination still happens on Opus 4.6. So generally speaking, it went pretty well. There was also no refusal issues yet because it wasn't yet known or popular that people were using LLMs for reverse engineering. So I believe Anthropic and OpenAI didn't know how to handle it yet because they didn't know that people were using it at the time. Through your research, in what way did you identify opportunities to inject more context semantic understanding for the LLMs beyond executive training? IDA. The way it changed the outcome regarding accuracy and expert collaboration. Haha, go dogs. Yes, go dogs. Yeah, so Brian, the way that we injected context was first through the function that they were currently looking at. So whatever the reverse engineer was looking at, that's also what the LLM saw. We also had experiments for seeing if we gave all of the connected functions next to it, which is something common that agentic models do now, where they'll look for everything in the neighborhood. That neighborhood awareness actually does a lot for benefit, but it can quickly degrade context if there are too many, which I think is kind of intuitive. So regarding accuracy, right, that was one way to get a bit of improved accuracy. However, I emphasize again that specific decompiler failures, like that line I showed, can derail an LLM regardless of how much context it gets. So it really requires studying of what are the error cases, because again, LLMs aren't actually trained on IDA, and IDA can change over time quickly. So it takes a lot to know what will actually cause it to fail. From Jonathan, thanks. I'm interested to hear the results of your follow-up work. Yes, we hope to do a lot of the follow-up work. This is something I'm going to be doing in my own lab at the University of Georgia, is how can we do this autonomously? We're working on this as a collaboration with others as well. How does this autonomous work, or how do these different context injections and models work when people reverse engineer? Any other questions? These are awesome questions. Thank you very much, all. I really appreciate them.